Hello, my name is Chris Holtzclaw, Senior Engineer for Figure Engineering and Project Lead on this current SBIR project, modernizing CPS for widespread benefits. Today I will be discussing some of the improvements we have planned, give an overview of our technological solution, and discuss the benefits our solution will provide for the Navy's collective protection system, commonly referred to as CPS. I will discuss our transition approach, along with partnering opportunities to help implement our technology into the Navy. I will end by explaining how our technology can be proliferated in other areas in the armed service and commercial sector to generate an even greater advantage. But first, let me give a quick introduction to our company, Figure Engineering. Figure Engineering is located in Lorton, Virginia, which is very close to the DC Naval Yard, Indian Head, and Norfolk Naval Base. Our facility is fully outfitted with 6,000 square feet of research and development space where we design, build, and evaluate mechanical smart systems, perfect prototypes, develop new materials, conduct testing, and much more. Our key focus areas include sensor integration, custom PCB design, hazardous material detection and mitigation, and polymer development, particularly in the area of 3D printing. We are a small but growing company who enjoys the challenge of designing, developing, testing, and commercializing novel solutions that meet the needs of our customers. Now let's move on to the next slide where I will talk about the particular challenge the Navy has given us to solve under this SBIR effort. A collective protection system, CPS, creates a protected zone or zones within a ship that provides protection to its personnel from chemical, biological, or radiological threats. This protection is achieved by supplying a surplus of air through a filtration system to cause overpressurization in a particular zone or zones. For example, the LPD-17 has 4 zones that will require a surplus of airflow. The access to the area is controlled via sealed airlocks to ensure zones remain safe and secure, especially in a threatening environment. The CPS is seamlessly integrated with the shipboard ventilation system, thus providing all supply air to the zone. To ensure personnel are protected from SBIR threats, the collective protection system uses significantly more air than standard shipboard ventilation. Due to the full-time positive pressure requirements in the CPS zones, the system's single operating mode consumes a significant amount of energy. In combination to an increased air supply, the energy required to provide adequate heating, ventilation, and air conditioning is proportionally high. Furthermore, the system relies heavily on human interaction for proper operation. Manual inspection and data logging from numerous points in each zone result in lengthy crew contact times to monitor and maintain the system. Without a centralized CPS control, both system response awareness and service optimization opportunities are limited. The key focus area of this effort is to design, develop, and implement an advanced, modernized, energy-efficient CPS solution, where the functionality and health of the system can be monitored and controlled from a centralized location. The newly developed solution needs to reduce energy consumption, crew workload, and operational and maintenance costs. The advanced CPS, outfitted with centralized controls, will need to provide enhanced system awareness and optimization through data analysis. The solution should also be flexible enough to enable future improvements without requiring a full system overhaul. To overcome the challenges and to meet the improvement targets, Figure Engineering has proposed and is in the development of a smart CPS VSD solution. We have designed a smart, modernized CPS equipped with a variable speed drive, advanced modern sensors, a PLC, and redundant HMIs. The PLC system will be outfitted with our advanced continuous time-adaptive ventilation system, called ACTAV, which controls the ventilation to maintain safe SBIR conditions and allow for future automation. By incorporating a PLC-driven variable speed drive into the system, we will reduce energy costs up to 50% while maintaining the required ventilation rates. The system will be equipped with a suite of advanced and robust sensors to monitor each zone. The inputs from these sensors will feed into the centralized CPS control to allow for user-centric, data-driven controls and real-time value-added feedback. Our system will collect, distill, and display key metrics for system optimization that can lead to efficient preventative maintenance planning and enhanced system response awareness. The concept aims to reduce system downtime and required manpower for monitoring and maintaining the CPS. To recap, our system will provide the Navy with a smart CPS VSD solution that has a data management component to optimize system health, an intelligent HMI interface that is user-centric, a PLC-based control that allows for future expansion, and robust sensor technologies to capture and deliver value-added information. In comparison to the legacy system, our smart CPS solution will provide centralized control to maintain SBIR threat protection. It is able to accept new robust sensors, is capable of future autonomy, and is energy efficient. Collectively, these benefits will help reduce energy and lifetime sustainment costs, reduce the operator workload, reduce the maintenance burden of the system, and future-proof the system for periodic component upgrades, all while maintaining effective SBIR threat protection. Now let's move on to the next slide, and I'll explain where we are in the technology development process and what we have planned for the upcoming project phases. We are currently in an 18-month SBIR Phase 2 base contract that has 2 future year-long options. In this base effort, we have constructed 2 small-scale zones that resemble zones in a CPS. Each zone is outfitted with the necessary equipment to represent an actual shipboarded CPS. We have already performed extensive testing and sensor selection on the small-scale zones and have begun the development of our source code that will integrate the smart conditions into the PLC and HMI system, which will lead to the development of a user-centric control to optimize operations. In parallel, we will continue to harden the interface to prevent unnecessary software and hardware issues. In option 1, we will plan on integrating and performing long-term testing of our smart CPS VSD solution at Indian Head CPS test facility, where we will continue to test, monitor, and fine-tune the system. During our second option, we will work with groups like PMS 317 to finalize system requirements and prepare plans for possible temp alt or retrofit in an LPD 17 or similar vessel. For our technology to be transitioned to the fleet, our selected hardware will need to meet certain mil-spec shock, vibration, and EMI requirements through testing. After our system has been verified and validated, we will be in a position to conduct long-term operational testing through an approved temporary alteration or temp alt plan. Now, if the Navy deems the operational risk of our technology is low and waives the temp alt, we will develop a retrofit plan illustrating how to implement our technology into the existing fleet. In post-Phase 2 efforts, we will execute on either the temp alt to secure operational test data for system validation, or, should the temp alt not be required, we will move to execute the retrofit plan to begin retrofitting the existing fleet with our technology. In parallel, we will work with key stakeholders to implement our smart CPS solution into new construction and future ship class designs. The work necessary to reach a successful implementation cannot occur in a vacuum. We will have to work proactively with multiple transition partners, which I will cover in the next slide. To make this effort successful, we have and will continue to partner with Navy's CPS lab at Indian Head to develop technology for shipboard use. To ensure the modernized CPS hardware is hardened against shock, vibration, and EMI, we will partner and work closely with Navy CPS labs and the Naval Surface Warfare Center, Philadelphia, for testing and evaluation requirements in both a non-operation and operational environment. Afterwards, we will look to the Joint Program Executive Office for Chemical and Biological Defense to approve our CPS modernization system. We will work with PEO ships such as PMS 443 or PMS 317 to update CPS system requirements and specifications for the updated CPS installation in new and existing ships. Finally, we will seek out partnership agreements with prime shipbuilders to license the SBIR-developed CPS technology. And as always, we will look for new opportunities to continue development and adapt our smart CPS VSD solution on other ship classes and non-ship platforms as a service for DoD organizations for widespread benefits. Our smart CPS VSD expansion technology, with appropriate modifications, has the ability to transition to other classes of ships in the Navy, along with other systems seeking advanced ventilation controls to protect personnel from hazardous airborne threats. There are many applications and systems this technology can enhance. Additional applications include, but are not limited to, fixed government buildings, armored ground vehicles that are hermetically sealed, public transportation facilities, chemical production plants, and other industrial processes where hazardous dusts or gases are generated. Thank you for listening. We are excited to provide a cost-saving smart solution to the Navy to help them improve their CPS system while continuing to safeguard against SBIR threats to keep their personnel protected. If you have any questions or would like to discuss any upcoming opportunities, you can reach me at the email address or phone number shown on the slide. Thank you again. Fair winds and following seas.